I want to welcome all of you to this workshop, and I just found out this morning that I'm chairing the first session. If those of you who don't know, I am Balakrishnan Medwala. I used to be a postdoc here with Alex, and so it's great to be back by time, as always. So the workshop is organized into a series of sessions, and in each session, speakers get 20 minutes, and after that we have a panel discussion. And the discussion leader of the panel discussion will make a final summary presentation on Wednesday afternoon. So this session on media-body interaction starts with the first speaker, Arghavan Safavi Naini, and so she will have the full 20 minutes, and if you have any questions, that can be deferred to the panel discussion.
So I'm going to talk mostly about applications of numerical techniques, and in particular, I've been working very closely with an experiment at NIST in Boulder. So this is John Bollinger's experiment. They have a two-dimensional array of trapped beryllium ions. And what I'm going to show you is how we have been trying to use a whole array of numerical techniques and theoretical tools to benchmark this particular simulator, and then try to use it for different types of applications. In particular, what we have been focused on lately is to be able to create states that are going to be useful for quantum-enhanced sensing. So what we have been very good at up until now is the ability to probe the quantum nature of single particles. So in particular, Serge Haroche and Dave Wineland, they won the Nobel Prize for being able to manipulate trapped ions or photons in cavity, isolate them very well from the environment, and have extremely good control on them. So this has really helped us make extremely sensitive atomic clocks, very good single qubits, and quantum sensors. So what we can compare this to is that we now have a lion or a cat, and now we can tame the lion. But now the question is, now that we have these very good atomic clocks, how can we make them better? So usually the problem is that we try to make them better by increasing sort of the signal-to-noise ratio, and what we do in particular in the optical lattice clock, for example, at JILA, is that we just try to probe larger and larger ensembles of atoms. But what we are hoping to do is to go beyond this and make better sensors and clocks by using the interactions in these systems, and use the interactions to actually generate entanglement between the particles, and these multipartite entangled states, such as the cat state that you're familiar with, are often very good for sensing very small, for example, magnetic fields and so on. So the system I'm going to talk about today is the trapped ion quantum simulator, and let me briefly tell you how it works. So what we have, or what they have in the experiment at least, is a stack of electrodes. They use a penning trap at NIST Boulder. So there's a stack of electrodes, there's a very large magnetic field, and there is an ion plasma that rotates in this very large magnetic field, and is confined because of the Lorentz force. So there is some confinement because of the electrode, and then additional radial confinement because of the Lorentz force on it. What they can do is they can actually apply spin-dependent forces onto the ions, and they can make these crystals of the ions that are between 20 to hundreds of atoms. So these are in situ pictures that I'm showing you, and as you know, if you have n ions, you'll have n axial modes. So what we care about is these particular axial modes that are transverse to the plane of the crystal. And by applying a spin-dependent force, we can couple the internal spin of the ion to the motional mode of the crystal. So depending on how you drive the ions, you can couple to only a single mode or to many of these modes. The regime that this experiment operates on is such that the drive basically is very close only to the center of mass mode. So if you now couple everything to the center of mass mode, you see that this mode is very uniform. The Hamiltonian is may be very familiar to you. It's a very, very typical sort of a spin boson model, where here we have the phonon position operator that couples to the collective spin of the ions. So what we wanted to do as a first step was to be able to benchmark that this particular system actually followed this Hamiltonian that one theoretically derives. And what I'm going to show you is that this is a very good testbed for a variety of numerical algorithms that one can develop that might not be exact. So why is this true? The reason is that the particular Hamiltonian that I just discussed is a type of Hamiltonian that doesn't explore the entire Hilbert space. And in fact, it only operates in a very small part of the Hilbert space. And this is because of this uniform coupling between the spins and the bosons. And because of this collective nature, actually, we can also develop global measurements that provide us very detailed information about the system. And this way, without doing, for example, full state tomography, we can actually get very fine-grained information. So the particular types of techniques we use are exact algorithms that use the permutation symmetry of the system, and we can solve the master equation then more efficiently. We use MPS-based methods for the full spin boson model. And finally, we have developed some semi-classical approaches that are not exact, but are very numerically efficient. So let me tell you a little bit about the semi-classical method that you might be the least familiar with. So this is the so-called truncated Wigner approximation, and this is a discrete variant of the truncated Wigner approximation. So the truncated Wigner approximation works something like this. You have an initial collective state of your spins, and as you know, for a particular state, if you have, for example, a spin coherent state, it points in a given direction, but you have some noise associated with the other two directions because you cannot, of course, measure all the three different spin directions very precisely. So here I'm showing you a spin coherent state. It has a Gaussian noise. And what we do is we can then say, okay, I can sample an initial state that is anywhere within this blob of noise. And then I can evolve each of these points in the distribution according to the mean field equation of motion. And then we can evaluate any observable by averaging over these different trajectories. So this allows us a way to, at a sort of a first level, include quantum noise into our mean field calculations. Now the discrete variant is very similar. Now the only difference is that we sample the noise on each spin 1/2 uncorrelatedly. So, and then we basically look at the trajectories of each of these particles. So let me show you a little bit of some of the results that you can get from different approaches. So the dynamics that I showed you are generated by, sort of the Hamiltonian that I showed you, the dynamics is generated by a propagator that you can separate into two parts. There is a first part that is the spin-phonon part of the propagator, and there's a second part that is the spin-spin part of the propagator. The spin-phonon part of your propagator is just a spin-dependent displacement. So what happens is that as time goes on, your phonon, so here I'm showing, for example, a vacuum state of the phonon, it displaces and it makes a circle in phase space. And every period, which is proportional to 1 over the detuning from your center of mass mode, it makes a full circle and comes back to the origin. So every period, this part of the propagator turns into an identity operator. So if you measure only at those times, and those times are, we call them decoupling points, what you will see is that you actually are measuring the dynamics of the Ising model. And here you have an now all-to-all Ising model, but your coupling is also proportional to inverse of your detuning. So here, as you can see, there is there are lines that I'm showing that are sort of dashed, and these dashed lines are the equivalent of the Ising model dynamics for the magnetization, but the solid lines are exact solutions using these MPS type of algorithms. And as you can see, there are specific times that these curves cross, and these are the so-called decoupling points. Okay, so I think I'm just sorry, this is a little bit of a... Okay, so now another question is, if you're away from this particular regime, where we have the all-to-all type of dynamics, what happens, and of course you can you can actually generate any type of effective spin model with this particular simulator. You can generate all sorts of parallel interactions, and then the simulations are a bit more challenging. And this is where we attempt to use these sort of semi-classical type of approaches that I showed you before. And as you can see, again, we have the exact solution that is shown in black. We have the dashed example with the truncated Wigner approximation, and we can do slightly better than the truncated Wigner approximation by taking into account up to third order cumulants, and then we recover again the exact result. And this is much more computationally efficient than the exact, because here you still only solve sort of polynomial order of equations that you're solving. Okay. So then the next step that we have tried to do in benchmarking our simulator is to add a transverse magnetic field to the model. So here we have now a non-commuting field that we add to the model. And then we first ask ourselves, is there a spin model description again, like what I showed you before, where at these decoupling points you recovered something like the Ising model? And what happens is that we find that at this stage there is really no particular description of a spin model description that is very good. And especially there is this regime if your magnetic field is of the same order as the detuning, where none of the spin models that you look at are good, and no perturbative Magnus expansion is good either. So this is the sort of regime where you have to actually account for the spins and the bosons on the same sort of order of importance. And this is actually a regime that we are interested in because this particular model has dynamical phase transition, and it's also classically chaotic. So here I'm showing you some sort of Poincaré sections for the classical Dickey model, and you can see that it has two separate phases as you change the relative strength of the spin-phonon coupling to the transverse field, where you go from an integrable phase to an ergodic phase. Okay. So on the sort of a parallel front, the quantum case, you can classify the phases of your model as normal and superradiant. You can, for example, look at if you do a quench experiment where you quench the transverse field according to some ramp profile and simultaneously measure some order parameter of your model, you see that you can probe now the dynamical phase transition that goes from the normal to the superradiant phase. Now in the normal phase of the Dickey model, the ground state is very similar to the transverse field Ising model, but now you also have the phonon. So the ground state in the large B is just all the spins pointing along the transverse field direction and having no phonons present. But if you have a very small field, the state that actually is your ground state is some type of a spin phonon cat state. So it's a macroscopic superposition of two states that are composed of your spins and your phonons. So here you have a paramagnetic spin and vacuum phonons. Here you have ferromagnetic spins and coherent state of the phonons. And this is the cat state that if you can, in principle, use this particular simulator to generate, it will be great. It would be great for various metrological applications. So let me show you another example of theory experiment comparisons that we did. So here are some particular ramp profiles that the experimentalist implemented. It's just a linear. One is just a linear ramp over 2 milliseconds, and the other one is an exponential ramp of the transverse field, also over 2 milliseconds. What we measure in this case is an absolute value of Sz and the Sx component of the magnetization. We have also measured the full spin distributions. So here you see there is so on the left you see here are the experimental plots of the full spin distribution. And you can see that, for example, in the large magnetic field regime, you have this peak at 0, while as you cross the critical point, where I'm showing it using the black line, you end with this double peak structure that is signature of the ferromagnetic spin state that I was showing you before. And on the right, you see the theory comparisons. And of course, the comparison, I mean, is not amazing. Because there's all sorts of decoherence phenomena that are happening in the experiment. But we can also look at the sort of a cut through these particular, so basically we can look at the magnetization now instead, and what we see is that we can compare now the experimental data with our theoretical prediction that I'm showing using the dashed black line, and this actually includes the decoherence with the decay model, but you can also compare it to if I only simulated the transverse field easing model, which is the faint dashed line. And as you can see, treating both the spins and the phonons is quite important to be able to benchmark the dynamics that this particular simulator generates. So let me quickly conclude. So what I showed you are a series of experiments where we were able to use theoretical tools that relied a lot on numerics to benchmark a trapped ion simulator with roughly hundreds of ions. Sorry. I don't know why this is not. So this, yeah, actually it's fine. So what I didn't show you is actually that we also did the first measurement of scrambling of quantum information in the same particular simulator. And we also took steps towards quantum enhanced metrology by looking at a particular system whose ground state is actually a spin phonon cat state. So what I've shown you so far is that, what I want to emphasize is that the theoretical techniques that I used are applicable to a diverse set of systems. If you have similar Hamiltonians, you will have same physics. So in particular, these particular approaches should be relevant for Rydberg atoms and MR systems, and we have also applied them to various experiments with atoms in cavities. What we are pursuing right now are basically looking at connections between classically chaotic dynamics and their signatures in the quantum dynamics of the system. We are trying to create more efficient tools for treating decoherence. This is something that we are really lacking in this sort of treating spin boson dynamics, including decoherence, in an efficient way. And finally, what we really want to do is we want to apply these techniques to a diverse set of systems. And our main goal is to have robust entanglement generation protocols. So this involves basically understanding the role of contact, dipolar, or boson-mediated interactions, understanding decoherence, and also finding new entanglement witnesses that are accessible experimentally and that allow us to theoretically benchmark the system. Thank you.
Thank you for keeping the
time.
And so, in fact, I think we have,
I have 2 minutes.
A couple of extra minutes. If anybody has any quick question, and I think we can use that time. If not, yes.
Maybe.
Okay. So, sorry, I didn't actually understand which simulation methods you used.
Oh, so I used all of them.
All of them? But MPS doesn't work very well in 2D, but you showed it 2D.
But it doesn't matter because the interactions are actually mediated by the boson, so the dimensionality of the system is sort of irrelevant. So if you do the spin model, it is a two-dimensional system, but for the boson-mediated, the dimensionality doesn't matter. What really matters is sort of how many boson modes you have, and what the cutoff on the boson mode you have to use.
I see.
Yeah.
Okay. And then truncated Wigner and MPS are sort of exactly in opposite regimes,
yep.
right?
So the truncated Wigner, in my opinion, works well. Works well in the regime where your system is very much Ising-like, and so basically, the addition of transverse field generally doesn't help with the truncated Wigner sort of agreement, but also truncated Wigner is only good for certain observables. So the higher order the observable you have, the worse truncated Wigner is going to work. But it's true that, so it's hard to say. So it's not exactly truncated Wigner, it's a discrete version of the truncated Wigner, but it's very hard. Yeah, but it's also very hard for that to a priori say if it works or not. And then also the additional improvements that I've done also are not very controlled. So it's always a little bit hard for these methods to say if they're going to work well or not.
Let's come back to that.
Yeah.
Okay, sure.
Hussein, do you have any comments?
Yeah.
With decay model comparison with John's experiment,
Yeah.
if we bring the slide,
Yep.
it's here. So we have decoherence in the
Yeah.
the
We have decoherence in this black dashed line.
referring to this.
No, on these ones, no.
So the lines shouldn't they be sharper or not?
Hmm?
Shouldn't the lines be sharper
I think why?
because you don't have decoherence?
But oh, our lines are sharper, though. What do you mean? Here? But so we have fewer, less population.
More visibility.
Maybe I don't understand what you're saying.
Shouldn't the signal be more visible?
Um.
The experiment seems to show.
Yeah. So the experiment, I think, has. You mean, for example, initially, yeah. So there is. Yeah. So I think there is a little bit of. So for example, they think there are stray fields in the experiment which we haven't accounted for, and we were not sure of the magnitude. So I think there are imperfections in the experiment that we don't know.
Okay.